Lecture 30, Capacitors in Series and Parallel. The objective of the lecture is to understand how multiple capacitors behave when they are connected in a circuit. So let's start with capacitors in series. So the capacitors are said to be in series if they are connected one after another. For example, there are three capacitances in this circuit having capacitances C1, C2 and C3, and they are connected one after another. The next condition is that same current is flowing through all the three capacitors. So the key observations are that the charge is same through all the capacitors and the voltage is distributed. So let's derive the equivalent capacitance. So we know that the formula for charge is simply C into V. And since the charge across each capacitance is same, therefore Q will be simply equal to C1 V1 will be equal to C2 V2 will be equal to C3 V3. And the total voltage in a series combination is simply V1 plus V2 plus V3. And substituting value of V1, V2, V3 from this equation, we get Q by C1 plus Q by C2 plus Q by C3. So here Q can be taken as common. So we get 1 by C1 plus 1 by C2 plus 1 by C3. Now rearranging this equation, we get V by Q is equal to 1 by C1 plus 1 by C2 plus 1 by C3. V is the total voltage and Q is the net charge. So V by Q will be simply equal to 1 by C equivalent, and that will be further equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is the general formula for equivalent capacitance in series. The important thing to note is the equivalent capacitance in series is always less than the smallest individual capacitance in that group. Now let's move on to capacitance in parallel. So the capacitors are said to be in parallel if they are connected across same two nodes. For example, in this case, there are only two nodes, suppose A and B, and all the entities are connected between two nodes. So we can see that the voltage across each capacitor is same, but the charge is distributed among each capacitor. The key observations are voltage is same, but the net charge will be simply Q1, Q2 and Q3. So let's derive the equivalent capacitance. The Q total will be simply equal to Q1 plus Q2 plus Q3. So we know that formula for Q is equal to CV. So Q total will come out to be simply C1 into voltage across this capacitance, that is V, plus C2 into voltage across this capacitor, that is V, plus similarly C3 V. V comes out, so it becomes equal to C1 plus C2 plus C3. Rearranging this equation, we get Q total divided by V is simply equal to C1 plus C2 plus C3. Net Q divided by net voltage is simply equal to C equivalent. So C equivalent comes out to be C1 plus C2 plus C3. Therefore, the general formula for equivalent capacitance in parallel becomes C1 plus C2 plus C3, so on up to all the capacitances connected in parallel. The equivalent capacitance in the parallel will be greater than the largest of the individual capacitor. So finally, if we summarize, charge in series connection is same, in parallel connection is different. Voltage in series connection is different, in parallel connection it is same. The formula is simply 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus so on. And here C equivalent will be C1 plus C2 plus C3 so on. Energy stored, that is half CV square, will be lower. Here it will be higher, and the final result will be that the C equivalent will be lower in series connection and higher in parallel connection. So we can use this formula to find out the equivalent capacitance in this question. The equivalent capacitance 1 by C equivalent will be simply equal to 1 by 4 microfarad plus 1 by 8 microfarad plus 1 by 4 microfarad, and solving it we get C equivalent is simply equal to 1 by 6 microfarad. Similarly here, the net capacitance will be simply sum of all the three values, that is 4 plus 8 plus 4 microfarad, and that comes out to be 16 microfarad.